Tonight, we're going to explore something you experience every single second of your life, yet cannot touch, see, or hold. Something so fundamental that without it, nothing would exist. Yet so mysterious that the greatest minds in history still argue about what it actually is. Time. You think you understand it. You check your watch. You remember yesterday. You plan for tomorrow. But here's the truth that will unravel everything you thought you knew. Time isn't what you think it is. Your brain has been lying to you about time since the moment you were born. Physicists have proven that time can stretch, compress, and even stop entirely. And the direction it flows, that might be the greatest illusion of all. By the end of this journey, time itself will feel like a stranger. Before we dive into this mind-bending exploration, if you find yourself fascinated by the deepest questions about reality, a quick like or subscribe would really help this channel continue making these kinds of journeys. It's a small gesture, but it means the world to me. Now, let's begin. Let me ask you something that sounds simple, but isn't. How long is right now? Not philosophically, practically. When you experience this present moment, this instant that feels so vivid and immediate, how long does it actually last? Neuroscientists have measured it. The German psychologist Ernst Poppel spent decades studying what he called the specious present, the window of time that our brains package together as now. And the answer is surprising. The present moment, as your brain constructs it, lasts about 2 to 3 seconds. That's it. Everything that happened more than 3 seconds ago is already being processed as memory. Everything more than 3 seconds in the future is anticipation. The vivid, immediate experience of now that you're having right at this instant occupies a window so narrow you could miss it in a few heartbeats. Think about what that means. You're not experiencing reality as it happens. You're experiencing a constantly updated reconstruction of reality assembled by your brain with a built-in delay. Your brain gathers sensory information, processes it, integrates it with expectations and context, and then presents you with what feels like an immediate experience. But by the time you experience anything, it's already the past. You are always, in a very real sense, living slightly behind the present moment. This might sound like a technical detail, but it reveals something profound about the nature of our experience. The present isn't a point in time, it's a construction, a span during which your brain collects data and weaves it into the seamless experience of now. And that construction is riddled with assumptions, shortcuts, and outright fabrications. Here's where it gets stranger. Different types of sensory information take different amounts of time to process. Sound travels to your ears and gets processed relatively quickly, in about 50 milliseconds. Visual information takes longer, about 100 milliseconds to fully process. Touch falls somewhere in between. If your brain simply presented information as it arrived, you'd experience the world as a desynchronized mess. You'd hear someone speak before you saw their lips move. You feel a tap on your shoulder before you saw the hand that did it. But you don't experience this desynchronization. Everything seems perfectly timed. Lips sync with voices. Sights match sounds. This is because your brain actively delays faster signals to wait for slower ones. It holds information in a buffer, lets everything catch up, and then presents you with a unified experience. The present moment you're experiencing right now is actually a carefully edited reconstruction assembled from events that occurred at slightly different times. This editing has limits. When the gap is too large, the illusion breaks down. This is why, When you watch fireworks from far away, you see the explosion before you, hear the boom. The time gap between light and sound at that distance is too large for your brain to paper over. But within certain thresholds, your brain seamlessly stitches together events that objectively occurred at different moments into what feels like a single, unified instant. Now let me tell you about something even more unsettling. Your brain doesn't just synchronize events, it actively reorders them. There's a famous experiment that demonstrates this. Researchers asked participants to press a button whenever they chose. After each button press, a flash of light appeared at varying delays. Participants were asked to report whether the flash seemed to happen before, during, or after their button press. The results were shocking. When the flash occurred about 100 milliseconds after the button press, people reported it as simultaneous with the press. That makes some sense given processing delays. But here's the strange part. When the flash occurred about 80 milliseconds before the button press, people still reported it as simultaneous or even as coming after the press. Read that again. The flash happened first. Then they pressed the button. But their brains presented it to them as button press first, then flash. Cause and effect got reversed in their subjective experience. Your brain can take events that actually happened in one order and present them to you in a different order. It does this constantly without your awareness, whenever it serves the goal of creating a coherent narrative. The timeline you experience is not the timeline that actually occurred. It's an edited version, rearranged for coherence. This leads to one of the most unsettling questions in neuroscience. If your brain routinely reorders events in time, how can you trust your sense of cause and effect? When you decide to move your finger and then your finger moves, did your decision really come first? Or did your brain edit the sequence after the fact to make it seem that way? In the 1980s, neuroscientist Benjamin Libet conducted experiments that haunted philosophers for decades. He asked people to move their wrist whenever they felt like it, and to note the exact moment they became aware of intending to move. Meanwhile, he recorded their brain activity. What he found was disturbing. Brain activity associated with the movement, called the readiness potential, began about 550 milliseconds before people reported being aware of their intention to move. The brain started preparing the action almost half a second before the person felt like they had decided to do it. This suggested that your conscious sense of deciding might be a retrospective construction. The decision happens unconsciously in your brain. Then, your brain generates the conscious experience of having made the decision and backdates it to make it seem like conscious choice came first. You feel like the author of your actions, but maybe you're just the narrator, telling a story about actions that were already set in motion before you became aware of them. Now, I want to be careful here because this is genuinely controversial. Some researchers argue that the readiness potential Libet measured isn't actually the decision itself, but rather just preparation or neural noise reaching a threshold. The neuroscientist Aaron Scherger has proposed that what Libet saw was random fluctuations in brain activity that occasionally cross a threshold and trigger movement, not some hidden decision-making process. Others point out that even in Libet's experiments, participants could consciously veto the action after the readiness potential began. The conscious self might not initiate actions, but it can still stop them. The debate continues, but what's not debatable is that our conscious experience of time is constructed. It's not a direct perception of objective temporal reality. It's an interpretation a narrative assembled from raw neural data. And that narrative doesn't always match what actually happened. Let me tell you about another quirk of time perception you've probably experienced without knowing it had a name. It's called the stopped clock illusion, or chronostasis. You glance at an analog clock with a second hand. For a moment, the second hand seems frozen, stuck in place for what feels like longer than a second, before it starts ticking normally. It's subtle, but once you notice it, you'll see it every time you look at a clock. Here's what's happening. When your eyes move quickly from one point to another, a movement called a saccade, your brain suppresses visual input during the movement. If it didn't, you'd experience a disorienting blur every time you moved your eyes. So your brain fills in the gap by taking the first clear image from your new fixation point and stretching it backward in time to cover the period of the eye movement. When you look at the clock, your brain takes that first image of the second hand and extends it backward to fill the gap left by the saccade. The result is that the first second you perceive seems abnormally long. The clock appears to pause before it starts ticking. This is your brain manipulating your perception of duration to create smooth, coherent vision. It's helpful. You don't experience jarring discontinuities every time you move your eyes, but it's also evidence that your experience of time is being constantly edited without your knowledge or consent. Here's an even more striking demonstration of constructed time. It's called the cutaneous rabbit illusion, and you can actually feel time being manufactured. If someone taps your wrist 3 times rapidly, then waits about a second, then taps your elbow 3 times rapidly, you'll feel exactly what happened. 3 taps at your wrist, pause, 3 taps at your elbow. Simple enough, but if the gap between the wrist taps and elbow taps is shortened to less than a second, something strange happens. Instead of feeling 3 taps at your wrist and then 3 at your elbow, you feel a series of taps hopping up your arm from wrist to elbow. Your brain creates the sensation of intermediate taps that never actually occurred. Phantom touches in locations that were never touched. But here's the really weird part. The first tap at your wrist already feels like it's part of the hopping sequence, even though at the moment it occurred, your brain couldn't possibly have known that elbow taps were coming. The later events change your perception of the earlier ones, retroactively. Information from the future, from events that hadn't happened yet when the first tap occurred, somehow reaches back and modifies your experience of the past. This proves that what you experience as the present is actually a delayed construction. Your brain waits, gathers information from a window of time, and then assembles an experience that incorporates data from both before and after the nominal present moment. The now you experience is not a point. It's a span, a window, within which your brain collects and organizes information to create the illusion of a unified present. Now let's talk about why time doesn't pass at a constant rate for you subjectively. You know this intuitively. Remember being a child, how summer vacations seemed to stretch on forever. Those 3 months felt like an eternity of possibility and adventure. Now, as an adult, entire years blur together. Christmas comes around and you think, didn't we just do this? Where did the year go? This isn't just a feeling. It's a measurable phenomenon that psychologists have studied extensively. And the explanation reveals something profound about how our brains construct the experience of duration. One theory is called the proportional theory. A year represents a much larger fraction of a 5-year-old's life than a 50-year-old's life. To a 5-year-old, 1 year is 20% of everything they've ever experienced. It's a huge chunk of their existence. To a 50-year-old, a year is only 2% of their life. Proportionally, each additional year becomes a smaller and smaller fraction of total experience. Time seems to shrink as we accumulate more of it. But there's another factor that might be even more important: memory density. When you're a child, everything is new. Every experience is being encountered for the first time. Your brain has to pay attention to everything because it doesn't have established patterns yet. Each day is filled with novel experiences that require active processing and encoding. And here's the key insight: your brain seems to estimate duration based on the number of new memories formed. More novel experiences means more memory formation, which makes time feel longer when you look back on it. As you age, the world becomes familiar. Your brain becomes efficient. It recognizes patterns and stops paying close attention to things it's seen before. Monday blurs into Tuesday, blurs into Wednesday, because nothing distinguishes them in memory. Your brain doesn't bother encoding every familiar moment in detail. When you look back, there's less there. The time seems to have passed quickly because there are fewer memory markers. There's a phenomenon in memory research called the reminiscence bump. When older adults are asked to recall significant memories from their lives, they disproportionately remember events from between ages 15 and 25. This decade is overrepresented in autobiographical memory compared to other periods. Why? This is when identity forms. First love, first job, leaving home, discovering your passions, making lifelong friends. Everything is new. Everything is significant. Everything gets encoded with unusual density. These years feel long in retrospect because they contain so many distinct, vivid memories. After 30 or so, for many people, novelty decreases. Careers are established. Routines solidify. Fewer truly new experiences occur. The years start to blur together. What distinguishes your 37th year from your 38th? For many people, not much. And so time seems to accelerate. There's another effect called telescoping. Recent events feel further away than they actually are. Something that happened last month feels like it was ages ago. Meanwhile, distant events feel closer. Your college years, which might be decades past, feel like they just happened. This creates a strange compression of the past where everything seems both too recent and too long ago. Neurologically, there may be additional factors. Dopamine production naturally decreases with age. If dopamine regulates the internal clock, lower dopamine means a slower internal clock, which means subjective time passes faster. The same objective hour contains fewer subjective moments for a 60-year-old than for a 20-year-old. But here's the hopeful part. You can fight this acceleration. The key is novelty and attention. Seek new experiences deliberately. Travel to places you've never been. Learn skills you've never tried. Break routines. Each novel experience creates a new memory marker, and more markers make time feel longer in retrospect. Practice mindful attention. When you're present and engaged with your experience, rather than lost in distraction or autopilot, time feels richer. Even familiar experiences can be made novel through close attention to details you normally ignore. Create distinct memories, take photographs, but also take mental snapshots. Notice things, create rituals that mark time. The more distinct events you can recall from a period, the longer that period will feel. A year of routine and autopilot will feel like it vanished. A year of novelty, attention, and distinct experiences will feel substantial, even long. You have some control over how quickly your life seems to pass. The question is whether you exercise it. This is why vacations often feel long while you're on them, but short in retrospect. While traveling, everything is new and your brain is actively encoding experiences. You're paying attention. Time feels full. But if the vacation was relaxing but uneventful, when you look back, there might not be many distinct memories to anchor the duration. The weeks seem to evaporate. Conversely, a period filled with intense, varied experiences can feel like it lasted forever when you look back, even if it passed quickly in the moment. People who have lived through wars or major life upheavals often report that those periods seem much longer in memory than the quiet years that followed. There's another model of time perception called the pacemaker accumulator model. It proposes that your brain has something like an internal clock, a neural pacemaker that generates regular pulses. These pulses are collected by an accumulator, and the number of pulses accumulated is what creates your sense of duration. This model explains some interesting phenomena. When you're paying close attention to time, more pulses get accumulated and duration feels longer. When you're absorbed in something else, pulses are missed or not accumulated, and duration feels shorter. This is why watching the clock makes time drag while being fully engaged makes it fly. The model also explains the effects of various substances and states on time perception. Stimulants like caffeine or amphetamines seem to speed up the internal pacemaker. More pulses are generated per objective second, so time feels like it's passing more slowly. You feel like you have more time. Depressants have the opposite effect, slowing the pacemaker and making time feel faster. Body temperature also affects the pacemaker. When you have a fever, your internal clock runs faster, and time seems to slow down. Studies have shown that people with elevated body temperature overestimate the passage of time, suggesting their internal clock is generating pulses more rapidly. Cannabis has particularly interesting effects on time perception. Users consistently report that time seems to slow dramatically while intoxicated. Minutes feel like hours. This appears to be related to disruption of dopamine signaling, which plays a crucial role in the pacemaker accumulator system. The drug doesn't just alter mood, it directly interferes with the mechanism by which we construct our experience of duration. Let me go deeper into the neurochemistry because it reveals just how physically constructed our experience of time really is. Dopamine is the key neurotransmitter in temporal perception. It doesn't just affect mood and motivation, it literally controls the speed of your internal clock. When dopamine levels are high, the pacemaker runs faster, generating more pulses per objective second. Time feels slower because more subjective moments are packed into each clock second. When dopamine is low, the pacemaker slows, fewer pulses accumulate, and time seems to speed past. This explains the effects of various substances on time perception. Cocaine and amphetamines flood the brain with dopamine. Users report that time slows dramatically. Hours feel like they contain more experience than usual. The internal clock is running hot, clicking off pulses at an accelerated rate. Caffeine has a milder version of the same effect. That morning, coffee doesn't just wake you up. It subtly shifts your perception of a duration. The hours before lunch might feel slightly longer than they otherwise would. Psychedelics like psilocybin produce profound alterations in time perception. Users describe the dissolution of normal temporal boundaries, an experience of eternal present, moments that seem to contain infinities. Brain imaging shows that psychedelics disrupt the default mode network. The brain regions responsible for our sense of self and narrative continuity. When that network quiets, the normal packaging of experience into sequential moments breaks down. Clinical conditions affecting dopamine have predictable effects on time perception. People with Parkinson's disease, which involves the death of dopamine-producing neurons, often have severe timing deficits. They struggle to estimate intervals, coordinate rhythmic movements, or perceive musical tempo. Time becomes slippery, hard to grasp. ADHD is increasingly understood as involving time blindness. People with ADHD often have genuine difficulty perceiving how much time has passed, how long tasks will take, or how to allocate time to activities. This isn't laziness or poor planning. It's a neurological difference in how duration is processed. In the 1930s, a researcher named Hudson Hoagland noticed something strange when his wife was sick with a fever. She complained that he had been gone for ages when he had only left the room for a few minutes. Intrigued, he conducted experiments and discovered that elevated body temperature speeds up the internal clock. When you have a fever, your subjective time runs faster than objective time. You overestimate how long intervals have lasted because your pacemaker is generating more pulses per second. Temperature, neurotransmitters, drugs, and disease all affect the clock. The lesson is clear. Your experience of time is a biological construction, susceptible to manipulation by anything that affects brain chemistry. There's nothing absolute about how long a minute feels. Let me talk about one more phenomenon that reveals how malleable our time perception really is. It's the experience people report during moments of extreme danger or stress. Time seems to slow down dramatically. People in car accidents describe seeing everything in slow motion, having time to notice tiny details, feeling like the crash took much longer than it actually did. For decades, scientists wondered if this might be an actual acceleration of mental processing. Perhaps in emergencies, the brain speeds up, taking in more information per second, effectively slowing down experience time. The neuroscientist David Eagleman tested this directly. He had people free fall from a tower while watching a display that flashed information too quickly for normal perception to read. If their brains were actually speeding up during the fall, they should have been able to read the display. The information should have appeared to slow down along with everything else. They couldn't read it. The information was still too fast. Their brains weren't actually processing faster. What happens instead is this. During moments of extreme fear, your amygdala takes over and forces your brain to record everything. Normally, your brain is selective about what it encodes, filtering out routine details. But in emergencies, the filter comes off. Every detail gets encoded into memory with unusual density and vividness. When you recall the event later, all those extra memories create the sensation that the event lasted longer. You remember more details than you would from an equivalent period of normal experience. So you infer that more time must have passed. Time doesn't actually slow down during a car crash, but your memory of it feels stretched because so much more was recorded. Emotion doesn't just color our experience, it warps our perception of duration in predictable ways. Depression makes time feel viscous, heavy, impossibly slow. Clinically depressed people consistently report that time drags, that hours feel like days, that each moment stretches painfully. This isn't just metaphor. When asked to estimate intervals, depressed individuals tend to overestimate how much time has passed. Their internal clock seems to be running slow, making objective time feel endless. Some researchers think this relates to reduced dopamine activity in depression. Others suggest that the lack of engagement with life, the absence of novel experiences and absorbed attention, makes time drag the same way boredom does. Whatever the mechanism, depression is partly a disorder of temporal experience. The future feels impossibly far away and not worth waiting for. Anxiety produces different distortions. Anticipated events seem to approach too quickly. The dreaded doctor's appointment rushes toward you, but waiting for results makes time crawl. Anxiety about the future makes the present unbearable. Each moment of uncertainty stretches as attention fixates on the passage of time. This is the watched pot effect. When you attend to time itself, when you monitor its passage rather than engaging with other things, each moment feels longer. Your attention accumulates more pulses. Duration expands. This is why waiting rooms feel eternal, and why checking the clock makes boring meetings even worse. The act of monitoring time makes time slow down. Positive emotions have the opposite effect. Joy and engagement make time fly. This is flow at work. When you're absorbed in something meaningful, when challenge and skill are balanced, when attention is fully engaged, the monitoring of duration stops. Hours vanish. You look up from your work and can't believe the day is gone. Trauma creates its own temporal distortions. Post-traumatic stress disorder involves the past invading the present. Flashbacks aren't just memories. They're experiences of being thrust back into a previous time, of reliving events as if they were happening now. The normal boundaries between past and present break down. Time becomes fractured. Some trauma survivors describe dissociation, a sense that time has become unreal, that they're watching events from outside, that moments are disconnected from each other. The normal flow of experience breaks down into disconnected fragments. Meditation traditions have long known that attention affects time perception. Mindfulness practices, which involve attending closely to present experience, can make moments feel fuller, richer, longer. The rushing flow of distracted time gives way to a more spacious present. This is perhaps why contemplatives speak of finding eternity in the moment. They've learned to manipulate their temporal experience through attention. This is a perfect illustration of what we've been discussing. Your brain doesn't experience time directly. It constructs an experience of time from memory, attention, emotion, and expectation. And that construction can be wildly inaccurate in ways you'd never notice without careful scientific investigation. We evolved to experience time this way because it's useful for survival. A unified, coherent, continuous experience of time helps us navigate the world, predict events, and respond to threats. But usefulness isn't the same as accuracy. Our brains were built to survive on the African savanna, not to accurately perceive the fundamental nature of temporal reality. They give us a practical approximation, good enough for hunting, gathering, and avoiding predators. But when we try to use this practical approximation to understand what time actually is, we run into problems. Because the truth about time, the truth that physics has revealed over the past century, is far stranger than anything our brains evolved to handle. For most of human history, we assumed that time was universal. There was one time ticking along at the same rate everywhere, a cosmic metronome keeping the universe in sync. This seemed so obvious that it was barely worth stating. Of course, a second is a second is a second, whether you're here on Earth, on the moon, or at the edge of the observable universe. Isaac Newton made this assumption explicit in his Principia Mathematica. He wrote of absolute, true, and mathematical time which of itself and from its own nature flows equably without relation to anything external. Time, in Newton's view, was like an invisible river flowing at a constant rate through the universe, carrying everything along with it at the same speed. Your location didn't affect time, your motion didn't affect time. Time was the unchanging backdrop against which the drama of physics unfolded, separate from and unaffected by the events within it. This view matched our everyday experience. It felt obviously correct, and it worked brilliantly for predicting the motion of cannonballs, the orbits of planets, the tides, and everything else Newton cared about. For 200 years, physics operated on the assumption of absolute time. It was completely wrong. The first cracks appeared in the 1880s, when physicists Albert Michelson and Edward Morley tried to detect Earth's motion through the hypothetical luminiferous ether, the medium through which light was supposed to travel. They expected to find that light traveled at different speeds depending on which direction Earth was moving through the ether. They found nothing. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. This made no sense under the prevailing physics. If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 70 miles per hour. Velocities add. That's basic physics. Light should work the same way. If Earth is moving through space and you shine a light in the direction of motion, the light should travel faster relative to a stationary observer. But it didn't. Light traveled at the same speed, regardless of the motion of the source or the observer. Some physicists, including Hendrik Lorentz and Henri Poincaré, developed mathematical tricks to explain this strange result. Objects moving through the ether must contract, they suggested. Clocks must slow down. These were seen as real physical effects caused by motion through the ether. Then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that changed everything. Einstein approached the problem differently. Instead of trying to explain why light behaved strangely, he asked, what the universe must be like if light's constant? Speed is a fundamental law rather than a puzzle to be explained. His answer demolished Newton's view of time. Einstein's theory of special relativity starts with two postulates. First, the laws of physics are the same for all observers moving at constant velocity relative to each other. There's no privileged frame of reference. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. From these two simple postulates, Einstein derived consequences that violated everything humans had assumed about time and space for millennia. If the speed of light is constant for all observers, then time cannot be universal. Here's why. Imagine you're on a spaceship traveling at half the speed of light. You turn on a flashlight and shine it forward. According to Newton, someone standing still should see that light traveling at 1.5 times the normal speed of light, your velocity plus the light's velocity. But Einstein's second postulate says no. That stationary observer must see the light traveling at exactly the speed of light, not faster. How can this be? How can the same beam of light travel at the same speed relative to both you on the ship and the stationary observer when you're moving at different velocities? There's only one way. Time must be passing at different rates for the two observers. If you're moving very fast, time slows down for you relative to someone who's stationary. This isn't an illusion or a perception effect. Time itself actually passes more slowly for the moving observer. This is called time dilation. The mathematics are precise. The Lorentz factor describes exactly how much time slows down at any given velocity. At everyday speeds, the effect is infinitesimal, too small to measure. At 10% of light speed, time runs about 0.5% slower. At 90% of light speed, time runs about 2.3 times slower. As you approach light speed, time slows more and more, approaching a complete stop at light speed itself. This sounds like science fiction, but it's been verified experimentally countless times. In 1971, physicists Joseph Hafele and Richard Keating loaded atomic clocks onto commercial airplanes and flew them around the world, eastward and westward. When they landed and compared the flying clocks to identical clocks that had stayed on the ground, the clocks no longer matched. The differences were tiny, just hundreds of nanoseconds. But they precisely matched what Einstein's equations predicted. The moving clocks had experienced less time. The effect becomes dramatic at higher speeds. Muons are subatomic particles created when cosmic rays strike the upper atmosphere. Muons are unstable. They decay in about 2.2 microseconds on average. Given their altitude of creation and their speed, they shouldn't survive long enough to reach Earth's surface. The math doesn't work. They should decay high in the atmosphere. But muons reach the ground constantly. We detect them all the time. How is this possible? Time dilation. From our perspective on Earth, time passes more slowly for the muon because it's moving at nearly the speed of light. What's 2.2 microseconds in the muon's reference frame is stretched out to much longer in ours. The muon lives its normal lifespan, but from our frame of reference, that lifespan is dilated, giving the muon time to complete its journey to the surface. Particle accelerators confirm this daily. When particles are accelerated to near light speed, they live longer than identical particles at rest. This isn't a theoretical prediction anymore. It's a routine observation that physicists rely on for their experiments to work. Time dilation isn't just about motion. Einstein's general theory of relativity, published in 1915, revealed something equally strange. Gravity also affects time. General relativity showed that gravity isn't a force in the traditional sense. It's a curvature of space-time caused by mass and energy. When you feel gravity pulling you toward the Earth, you're actually experiencing the curvature of space-time around Earth's mass. And this curvature affects time. The stronger the gravitational field, the more time slows down. Near a massive object like the Sun, time passes more slowly than far from it. Near a black hole, where gravity becomes extreme, time slows dramatically. At the event horizon of a black hole, time stops entirely from an outside observer's perspective. This has been measured with extraordinary precision. In 1959, physicists Robert Pound and Glenn Rebka measured the difference in time between the top and bottom of a 22-meter tower at Harvard University. Using the Moosbauer effect to detect incredibly tiny frequency shifts in gamma rays, they found that time moved slightly faster at the top of the tower than at the bottom, exactly as general relativity predicted. Gravity was weaker at the top, so time ran faster there. The differences at the scale of a tower are minuscule, but they're real, and they have practical consequences. Let me tell you about GPS, because it is the most tangible proof that relativistic time dilation is not just real, but matters in everyday life. GPS satellites orbit about 12,500 miles above Earth's surface. They work by broadcasting extremely precise time signals. Your GPS receiver picks up signals from multiple satellites, and calculates your position based on the tiny differences in arrival times. For this to work, the timing must be accurate to within about 20 to 30 nanoseconds. Any error in the clocks directly translates to position error. Here's the problem. The satellites experience time differently than clocks on Earth's surface, for two reasons. First, gravity. The satellites are farther from Earth's center, so they experience weaker gravity. According to general relativity, weaker gravity means time runs faster. The clocks on GPS satellites tick faster than ground clocks by about 45 microseconds per day. Second, velocity. The satellites are moving at about 14,000 kilometers per hour in orbit. According to special relativity, this motion causes time to slow down. The orbital velocity makes the satellite clocks run slower than ground clocks by about 7 microseconds per day. The net effect is that GPS satellite clocks run faster than ground clocks by about 38 microseconds per day. 45 microseconds faster from gravity minus 7 microseconds slower from velocity equals 38 microseconds faster overall. That sounds tiny, but at the speed of light, 38 microseconds corresponds to a distance of about 11 kilometers. If GPS didn't correct for relativistic time dilation, your position readings would drift by roughly 10 kilometers per day. In a week, GPS would be completely useless for navigation. So every GPS satellite carries atomic clocks that are deliberately set to run slower than ground clocks by exactly the amount needed to compensate for relativistic effects. The satellites are programmed with Einstein's equations. The fact that GPS works, that you can navigate to within a few meters anywhere on Earth, is proof that time dilation is real. Near black holes, gravitational time dilation reaches extreme levels that challenge imagination. Imagine falling toward a black hole while a friend watches from a safe distance. From your perspective, you fall in finite time, crossing the event horizon and continuing toward the singularity. You experience hours, maybe minutes, depending on the black hole's size. Then you're destroyed by tidal forces or the singularity itself. But from your friend's perspective, something entirely different happens. They watch you approach the event horizon, but you never quite reach it. Your image reddens as light loses energy climbing out of the gravity well. Your movement's slow. Time for you, as observed from outside, approaches a standstill. You appear to freeze at the horizon, fading to darkness over billions of years. This isn't an optical illusion. It's genuinely what happens. From the outside perspective, you never cross the horizon because time stops there. From your perspective, you sail right through. Both perspectives are valid in their own reference frame. The movie Interstellar depicted this accurately. When astronauts visited Miller's planet, which orbited close to the massive black hole Gargantua, time dilation was so extreme that 1 hour on the planet's surface corresponded to 7 years passing on their mothership. Director Christopher Nolan consulted physicist Kip Thorne to ensure scientific accuracy. A black hole of Gargantua's mass really would produce time dilation of that magnitude. Neutron stars, the collapsed remnants of massive stars, also produce significant gravitational time dilation. A clock on the surface of a neutron star runs measurably slower than a clock far away. If you use GPS satellites around a neutron star, the relativistic corrections would be enormous. Not microseconds, but significant fractions of time. These extreme environments show that time dilation isn't a subtle effect relevant only to precision instruments. In strong gravity, Time becomes dramatically noticeably different depending on where you are. Let me try to help you feel the weight of what this means. Time is not universal. There is no cosmic clock ticking away at the same rate everywhere. Your time is not my time. The time in your basement is slightly different from the time on your roof because gravity is slightly stronger at lower altitudes. The effect is incredibly small at human scales, but it's real. If you spend your life living on the ground floor, you age slightly less than someone who lives on the top floor of a skyscraper. Not by enough to notice, but in principle, the difference exists. When you walk upstairs, you literally travel into the future relative to someone who stays on the ground floor. Not by much, an undetectably small amount, but it's happening. Your experience of time depends on where you are and how you're moving. There is no absolute time, no universal now, no single correct answer to the question, what time is it? This demolishes our intuitive sense of simultaneity. Consider this question. What is happening right now on a planet orbiting Alpha Centauri, 4 light years away? Your intuition says there should be an answer. Right now, at this very moment, something is happening there. And if we could somehow know instantly, we could find out what it is. But Einstein showed there's no such thing as right now at a distance. Different observers, moving at different velocities, will disagree about which events are simultaneous. What's happening now on Alpha Centauri depends on who's asking and how they're moving. Here's an example that physicists call the Andromeda paradox. 2 people pass each other on the street. One is walking toward the Andromeda galaxy. One is walking away from it. Because of their different velocities, they have different definitions of now. For the person walking toward Andromeda, the now slice of space-time at Andromeda might include events that are, by the other person's now slice, still days in the future. Different velocities mean different presents. This seems impossible. It violates everything we feel about time. But it follows directly from the physics. Simultaneity is relative, not absolute. Einstein himself addressed this in a letter to the family of his friend Michel Besso, written shortly after Besso's death in 1955. He wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. This wasn't poetry or philosophy, it was physics. The equations of relativity don't contain a special moment called now. All moments are equally real. What we experience as the flow of time is a feature of our consciousness, not of external reality. This leads to a view called the block universe. In this interpretation, past, present, and future all exist equally. The universe is a 4-dimensional block of space-time in which all events simply are. The Big Bang isn't gone. Your death isn't yet to come. They all exist eternally in the fabric of space-time. We experience time sequentially because of how our minds work, like reading a book 1 page at a time. But the whole book already exists. The ending is already written. We just haven't read it yet. As the saying goes, time is nature's way of keeping everything from happening at once. But in the block universe view, everything does happen at once, in a sense. We just experience it one moment at a time. Not all physicists accept the block universe interpretation. Some argue for a growing block universe, where the past and present exist, but the future is genuinely open, not yet determined. Others argue for presentism, where only the present moment truly exists. The debate is ongoing and touches on deep questions about the nature of reality, determinism, and free will. But here's what's not controversial. Our intuitive sense of time with its flowing present, vanished past, an open future finds no support in the equations of physics. Whatever time actually is, it's not what we perceive it to be. Let me push further into the strange. According to special relativity, as you approach the speed of light, time slows down relative to a stationary observer. At the speed of light itself, time stops entirely. Photons, particles of light, experience no time at all. This is hard to wrap your head around, but it follows directly from the math. From a photon's frame of reference, if we can even meaningfully speak of such a thing, its emission and absorption are simultaneous. A photon that left a star 1,000,000 light years away and enters your eye tonight. From that photon's perspective, those two events happen at the same instant. The photon experiences no journey, no duration, no passage of time. For light, time doesn't exist. In 2012, physicist Frank Wilczek proposed something that sounded impossible: a time crystal. A system that would repeat in time the way ordinary crystals repeat in space. Normal crystals have structure. Their atoms are arranged in regular, repeating patterns. They break spatial symmetry by preferring certain positions over others. Wilczek asked whether something could break time symmetry instead, spontaneously oscillating even at its lowest energy state. Most physicists were skeptical, but in 2017, researchers at Google and other labs actually created time crystals using trapped ions and other quantum systems. These systems oscillate indefinitely, repeating in time without absorbing or releasing energy. Time crystals don't violate conservation of energy. They're in their ground state, their lowest energy configuration. But that ground state involves periodic motion, a breaking of time's usual uniformity. What does this tell us? Time symmetry can be spontaneously broken. Time has structure that can crystallize. The physics of time is richer and stranger than we assumed. Time crystals are still being explored. They may have applications in quantum computing and precision measurement, but their deeper significance is what they reveal. Time is not just a backdrop. It's something that physical systems can interact with, break, and structure in unexpected ways. This has implications for how we think about the early universe. Just after the Big Bang, the universe was unimaginably hot and dense. Everything was moving at or near light speed. In some sense, time as we understand it didn't exist yet. There was no well-defined direction of time, no clear sequence of events. The emergence of temporal order, of before and after, is something that happened as the universe cooled and expanded. Time itself has a history, and time might have an end. Some cosmologists believe the universe will eventually reach a state of maximum entropy, a heat death where nothing ever changes again. If nothing changes, does time still exist? Or is time fundamentally tied to change, such that no change means no time? We'll explore this question more later. Let me tell you about one more consequence of relativity that might be the most mind-bending of all. Time travel to the future is not just theoretically possible, it's a straightforward consequence of physics we've verified in labs. If you accelerate constantly at 1g, the acceleration you feel from Earth's gravity, you could theoretically travel anywhere in the observable universe within a human lifetime. As your ship approaches the speed of light, time dilation compresses the journey. Years of your ship time correspond to centuries, millennia, or even millions of years passing in the outside universe. You could travel to the Andromeda Galaxy, 2.5 million light years away, in about 28 years of ship time. The catch? 2.5 million years would pass on Earth. Everyone you knew, every civilization you remembered, would be gone. Humanity might have gone extinct, evolved into something unrecognizable, or spread across the galaxy in forms you couldn't imagine. You'd return to a universe that had experienced millions of years of history, while you experienced less than 3 decades. This is not science fiction speculation. This is what Einstein's equations predict. It's been confirmed in every experiment that tested it. Time dilation is real. Astronaut Scott Kelly spent 340 days on the International Space Station. Due to the combined effects of his orbital velocity and the slightly weaker gravity at orbital altitude, he aged about 5 milliseconds less than his twin brother Mark, who stayed on Earth. 5 milliseconds is trivial, but it's real. Scott Kelly is genuinely, measurably younger than he would have been if he had stayed on the ground. If he had spent those days traveling at close to light speed instead of in low Earth orbit, the difference wouldn't be milliseconds. It would be years, decades, centuries. Let me work through a more dramatic example to show just how extreme time dilation becomes at high velocities. This is the famous twin paradox, though it's not actually a paradox at all. Imagine twins, Alice and Bob. Alice stays on Earth. Bob boards a spacecraft capable of traveling at 90% of the speed of light. His destination is a star 10 light years away. At 90% of light speed, the Lorentz factor is about 2.3. This factor determines how much time dilation occurs. For every hour that passes for Bob on his ship, about 2.3 hours pass on Earth. From Earth's perspective, the journey to the star takes about 11.1 years each way, for a round trip of about 22.2 years. Alice ages 22 years, waiting for her brother to return. But Bob experiences time differently. For him, the journey takes only about 9.6 years total because of time dilation. When he steps off the spacecraft, he's aged less than 10 years while Alice has aged over 22. Bob is now more than 12 years younger than his twin sister. Is this a paradox? From Bob's perspective, wasn't Earth moving away from him at 90% of light speed? Shouldn't Alice have experienced time dilation too? The resolution is that the situation isn't symmetrical. Bob accelerated to reach his high velocity, then decelerated, turned around, accelerated again, and decelerated to land. He felt these accelerations. Alice felt nothing. Bob changed reference frames multiple times. Alice stayed in a single inertial frame. This asymmetry is what breaks the apparent paradox. The twin paradox has been verified experimentally with atomic clocks on airplanes and satellites. The mathematics is correct. Time dilation is real. If you travel fast enough, you genuinely age less than people who stay home. Time travel to the future is physically possible. It's just engineering. Build a fast enough ship, or sit near a strong enough gravitational field, and you can skip forward in time. The universe will age around you while you experience only a fraction of that duration. Time travel to the past is another matter entirely. The equations of general relativity do permit mathematical solutions involving closed time-like curves, paths through space-time that loop back to earlier times. In principle, following such a path would take you into your own past. Physicist Kip Thorne showed that wormholes, hypothetical tunnels through space-time, could theoretically function as time machines, but most physicists are skeptical that backward time travel is actually possible. Wormholes, if they exist at all, would likely be unstable. Keeping one open might require exotic matter with negative energy density, which might not exist. Stephen Hawking proposed the chronology protection conjecture in 1992, suggesting that the laws of physics conspire to prevent backward time travel. When you try to create a time machine, quantum effects cause fluctuations that grow without bound and destroy the machine before it can be used. There are also the famous paradoxes. The grandfather paradox is the classic example. If you could travel to the past, you could potentially prevent your own birth. But then you wouldn't exist to travel back. These logical contradictions suggest that backward time travel might be impossible, not just technologically, but logically, ruled out by the structure of reality itself. Forward time travel? That's just physics. We can do it today, in tiny amounts. Every time you fly in an airplane, you travel slightly into the future relative to people on the ground. The universe doesn't care about our intuitions about time. It doesn't respect our sense that time flows, that the past is gone, that the future is unwritten. Physics describes a universe where time is flexible, relative, and perhaps illusory in ways our brains were never built to comprehend. Let me tell you about a number. 13.8 billion. That's approximately how many years the universe has existed. 13.8 billion years since the Big Bang. I've said that number, you've heard it, but you haven't understood it. Not really. The human mind cannot genuinely comprehend a number that large. Our brains evolved to deal with quantities we might encounter in daily life. A few dozen people in a tribe, a few hundred days of travel, a few thousand objects we might possess. These are the scales our intuitions handle. Billions? Billions are beyond us. Let me try to make this concrete anyway, knowing I'll fail. If you counted one number per second, without sleeping, without pausing, without ever stopping, it would take you about 32 years to count to 1 billion. Just 1 billion. To count to 13.8 billion. At one number per second, you'd need about 438 years. You'd need to start counting before Shakespeare was born and keep counting until today. Never pausing, never sleeping, just counting, and you'd finally reach the age of the universe. Here's another attempt. Imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at midnight on January 1st. December 31st at midnight is right now. In this cosmic calendar, galaxies begin forming in late January. Our Milky Way takes shape around March 15th. But our sun and solar system don't appear until September 1st. For more than 8 months of cosmic time, our solar system didn't exist. The universe went about its business, stars forming and dying, galaxies colliding and merging, and Earth wasn't even a possibility. Life appears on Earth in late September, but it's just single-celled organisms. For weeks of cosmic time, that's all there is. Simple microbes, nothing you could see with the naked eye. Complex multicellular life doesn't show up until December. Dinosaurs appear on December 25th, Christmas Day. They dominate the planet for about 5 days of cosmic time, then go extinct on December 30th. Everything you think of as recorded human history, from the earliest cave paintings to the smartphone you might be holding right now, occurs in the final 14 seconds of December 31st. The pyramids were built about 4 seconds ago. Jesus lived about 3 seconds ago. The Industrial Revolution was about half a second ago. Your entire life is a fraction of a second. This is the reality of deep time. The universe is ancient beyond comprehension, and we are recent beyond belief. How do we know the universe is this old? The measurement comes from multiple independent lines of evidence that all converge on the same answer. The cosmic microwave background radiation is the afterglow of the Big Bang, light released when the universe cooled enough for atoms to form, about 380,000 years after the Big Bang. We can measure the temperature and structure of this radiation with extraordinary precision, and from it, we can calculate the age of the universe. The expansion rate of the universe, measured by observing distant galaxies moving away from us, also gives us the age. Run the expansion backward, and you find that everything was together in a single point about 13.8 billion years ago. The ages of the oldest stars, determined by their composition and evolutionary state, are consistent with a universe that's about 14 billion years old. No stars older than the universe. That's a good sign we have the age right. All these independent measurements agree. The universe is approximately 13.8 billion years old. Before the 18th century, people had no concept of deep time. The Earth was assumed to be young. Sadidi, 1650, Archbishop James Ussher calculated from biblical genealogies that creation occurred on October 23rd, 4004 BCE. The Earth was less than 6,000 years old. This wasn't considered a religious opinion. It was accepted knowledge. The discovery of deep time was as revolutionary as the discovery that Earth orbits the Sun. It displaced humans from a special temporal position, just as Copernicus had displaced us from a special spatial position. The revolution began with geology. In the late 18th century, a Scottish farmer and naturalist named James Hutton looked at rock formations in his native Scotland and saw something that contradicted the young Earth view. He observed layers of sedimentary rock that must have taken vast ages to deposit, then tilt, then erode, then get covered by new sediments. The processes he could observe happening slowly in his own time: erosion, sedimentation, volcanic activity, were the same processes that had shaped these ancient rocks. In 1788, Hutton wrote that he found no vestige of a beginning, no prospect of an end. Earth's history stretched back incomprehensibly far, far longer than any biblical chronology allowed. Charles Lyell expanded on Hutton's work in his 1830 book, Principles of Geology. Lyell championed uniformitarianism, the idea that the present is the key to the past. The same slow processes we observe today, given enough time, could produce all the geological features we see. Mountains erode grain by grain, canyons carve inch by inch. Given millions of years, these tiny changes accumulate into vast transformations. This was radical. It required accepting an Earth almost unimaginably old. Darwin's theory of evolution depended on deep time. Natural selection produces large changes through accumulation of small variations over vast spans. Without Lyell's geology, without the gift of millions of years, Darwin's theory couldn't work. The Origin of Species, published in 1859, explicitly acknowledged this debt. But acceptance was slow. Deep time was emotionally disturbing. It made human existence seem brief and insignificant. It contradicted religious teachings about creation. It required imagining spans of time that had no precedent in human experience. Lord Kelvin, one of the most respected physicists of the 19th century, calculate that the Earth could be no more than 20 to 40 million years old, based on how long it would take a molten ball to cool to present temperatures. This seemed to refute the geologists and the Darwinists. Kelvin was wrong. He didn't know about radioactivity, which was discovered in 1896. Radioactive decay produces heat inside the Earth, keeping it warm far longer than Kelvin's calculations allowed. Once radioactivity was understood, it provided both the heat source that explained Earth's temperature and, eventually, the tools for measuring Earth's actual age. The discovery of deep time fundamentally changed human self-understanding. We went from being the purpose of a young creation to being recent arrivals on an ancient planet, in a universe far older still. Every generation since has had to grapple with what this means for human significance and meaning. Now let's zoom into Earth. Our planet formed about 4.54 billion years ago from the same cloud of gas and dust that formed the Sun. We know this through radiometric dating, measuring the decay of radioactive elements in ancient rocks. Uranium decays into lead at a known rate. By measuring the ratio of uranium to lead in ancient minerals, we can determine when those minerals crystallized. The oldest Earth rocks are about 4 billion years old. Meteorites, remnants from the formation of the solar system, date to 4.57 billion years ago. How do we know these ages so precisely? The answer is radiometric dating, one of the most powerful tools in all of science. Radioactive elements decay at constant rates. Uranium-238 decays into lead-206 with a half-life of about 4.5 billion years. Potassium-40 decays into argon-40 with a half-life of 1.25 billion years. Carbon-14 decays into nitrogen-14 with a half-life of 5,730 years. Half-life means that in one half-life, half of the original radioactive atoms will have decayed. In two half-lives, 3/4 will have decayed. The decay is exponential and predictable. By measuring the ratio of parent isotope to daughter isotope in a rock, scientists can calculate when that rock formed. If a rock contains equal amounts of uranium and lead, one half-life has passed, and the rock is about 4.5 billion years old. If it contains 3 parts lead to 1 part uranium, it's about 9 billion years old. Different isotopes work for different timescales. Carbon-14 is useful for dating organic material, up to about 50,000 years old, perfect for archaeology and recent geology. Potassium-argon dating works for volcanic rocks, from hundreds of thousands to billions of years old. Uranium-lead dating works for the oldest materials in the solar system. The beauty of radiometric dating is redundancy. Multiple isotope systems can be applied to the same sample. If they all give the same age, confidence increases, and they do agree consistently across different methods and different labs worldwide. Zircon crystals are particularly valuable. These tiny minerals form in volcanic rock and are incredibly durable. They incorporate uranium but exclude lead when they form. Any lead present in a zircon must have come from uranium decay after formation. The oldest zircons ever dated are 4.4 billion years old, nearly as old as the Earth itself. These aren't estimates or guesses, they're measurements based on fundamental physics. In the early days, Earth was a hellscape. The surface was molten rock. The atmosphere was unbreathable, filled with carbon dioxide, water vapor, and toxic gases. Asteroids and comets bombarded the planet constantly in what's called the late heavy bombardment. If you could somehow visit early Earth, you wouldn't survive a second. Life appeared surprisingly quickly once conditions allowed. The oldest confirmed fossils are about 3.5 billion years old. Stromatolites formed by colonies of bacteria. But there's chemical evidence suggesting life might have existed even earlier, perhaps as far back as 4 billion years ago, just a few 100 million years after Earth formed. Here's something remarkable to contemplate. The emergence of life seems to have happened almost as soon as it was possible. As soon as Earth's surface cooled enough for liquid water to exist, life appeared. This suggests that life might not be a rare cosmic accident. It might be something that emerges readily whenever conditions allow. We don't know for certain, but the speed of life's appearance on Earth is suggestive. But here's the thing. Life stayed simple for an incredibly long time. For roughly 3 billion years, life on Earth was just single cells, bacteria, archaea, nothing you could see without a microscope. No plants, no animals, no fungi, just microscopic blobs drifting in the oceans, doing little more than reproducing. 3 billion years. That's more than twice the time since complex life appeared. If you visited Earth for most of its existence, you find a planet that looks essentially barren. Blue oceans, brown continents, white clouds, but nothing obviously alive. You'd need a microscope to find the life that was there. Around 2.4 billion years ago, something happened that transformed the planet. Cyanobacteria evolved the ability to perform photosynthesis, releasing oxygen as a waste product. Oxygen was toxic to most existing life. What followed was the Great Oxygenation Event, sometimes called the oxygen catastrophe from the perspective of the anaerobic organisms that died. Oxygen accumulated in the atmosphere, rusted the iron in the oceans, and eventually created conditions that would allow for more complex life. But complexity didn't appear immediately. After the oxygenation, there's a period of about 1 billion years, sometimes called the boring billion, when not much seemed to happen. Life remained simple. We don't fully understand why. Perhaps oxygen levels needed to rise further. Perhaps other conditions weren't right. But for 1 billion years, life remained microbial. Then, about 541 million years ago, something changed. In a geological instant, complex multicellular life erupted. This is the Cambrian explosion, one of the most dramatic events in Earth's history. In perhaps 20 million years, a blink in geological time, animals with eyes, shells, legs, and teeth appeared for the first time. The oceans filled with diversity. All the major animal body plans we know today trace their origins to this period. We still don't fully understand what triggered the Cambrian explosion. Rising oxygen levels, the evolution of predation creating evolutionary arms races, the appearance of eyes which changed what was possible in evolution, the breakup of a supercontinent that created new ecological niches, probably some combination, but the timing is striking. Life was simple for 3 billion years. Then suddenly, in less than 1% of Earth's history, complexity exploded. The history of life isn't a story of smooth progress. It's punctuated by catastrophes, mass extinctions that reset the clock, and redirected evolution's course. There have been 5 major mass extinctions in the past 500 million years, each one a devastation that reshaped life on Earth. The first great dying came at the end of the Ordovician period, about 444 million years ago. Glaciation locked up water in ice sheets, dropping sea levels, and devastating marine life. About 85% of all species went extinct. Life had been confined almost entirely to the oceans then, and the oceans became killing fields. The late Devonian extinction, about 372 million years ago, killed roughly 75% of species over a prolonged period. The causes remain debated, but ocean anoxia, periods when oxygen levels in the seas dropped catastrophically, seems to have played a major role. The great armored fish and early reef ecosystems were devastated. Then came the worst catastrophe of all. The end Permian extinction, 252 million years ago, killed 96% of all marine species and 70% of terrestrial vertebrates. It's called the Great Dying for good reason. Life on Earth nearly ended entirely. The cause appears to have been massive volcanic eruptions in what is now Siberia, which released enormous amounts of carbon dioxide, causing global warming, ocean acidification, and anoxia. Recovery took 10 million years. The end Triassic extinction, about 201 million years ago, cleared the way for the dinosaurs. Before this extinction, dinosaurs were a minor group. Afterward, with their competitors eliminated, they diversified into the dominant land animals and remained so for over 160 million years. Finally, the end Cretaceous extinction, 66 million years ago, ended the reign of the dinosaurs. An asteroid about 6 miles across struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact triggered global fires, a prolonged winter from debris blocking sunlight, acid rain, and ecosystem collapse. About 76% of all species went extinct, including all non-avian dinosaurs. These extinctions are how geologists divide time. The boundaries between geological periods are often defined by mass extinction events. The KPG boundary, marking the end of the Cretaceous and the beginning of the Paleogene, is visible in rock formations worldwide as a thin layer of clay enriched with iridium, an element rare on Earth but common in asteroids. Each extinction took millions of years to recover from. New species evolved to fill empty niches, but biodiversity took 10 to 30 million years to return to pre-extinction levels. These are sobering timescales, and now scientists speak of a sixth mass extinction, one caused by humans. Current extinction rates are estimated at 100 to 1,000 times the natural background rate. Species are disappearing faster than at any time since the dinosaurs died. We are the asteroid this time, though moving in slow motion by geological standards. The fossil record teaches us that extinction is permanent and that recovery takes millions of years. What we destroy in decades will not return in human timescales. Fish appeared about 500 million years ago. Plants colonized land around 470 million years ago, followed by insects, then amphibians, then reptiles. Dinosaurs dominated from about 230 million years ago, until their extinction 66 million years ago. Mammals existed throughout the age of dinosaurs, but they were small, marginal creatures hiding in the shadows. After an asteroid impact ended the dinosaurs' reign, mammals diversified rapidly into the ecological niches left empty. Primates appeared about 55 million years ago. The great apes split off about 15 million years ago. Beings you would recognize as human, creatures that could look in a mirror and ponder their existence, have been around for maybe 300,000 years. Modern human civilization, with agriculture and cities and writing, is about 10,000 years old. Let me put that in perspective another way. If you watched a time-lapse of Earth's entire history, with each second representing 10,000 years, the movie would be about 5.25 days long. For the first 4 days, not much happens that you could see. Oceans exist. Continents drift. Sometimes there are ice ages, but no visible life on land. Nothing but empty landscapes and microbial seas. In the last day, things get interesting. Plants cover the land. Animals appear. Dinosaurs arrive and dominate for about 6.5 hours, then suddenly vanish. Mammals take over. In the final 3 seconds of the 5-day movie, humans appear. Everything you've ever heard of, every event in human history, every person who ever lived, every civilization that rose and fell, happens in the final 10th of a second. We're a flash, a blip, a momentary pattern in the endless churning of matter and energy. Geologists may soon officially recognize a new epoch. The Anthropocene, the age of humans, the period when one species became a geological force. What markers would future geologists find if they dug down to our era millions of years from now? First, a global layer of plastic. Microplastics now exist in sediments worldwide, from ocean floors to mountain lakes. This layer will persist in rock formations for millions of years, a clear signature of our age. Second, radioactive isotopes. Nuclear testing in the 1940s and 50s deposited distinctive isotopes like plutonium-239 and carbon-14 around the globe. The spike in 1945 is detectable everywhere and makes an excellent stratigraphic marker. Third, concrete and metal. We have produced enough concrete to cover every square meter of Earth's surface in a kilogram of the stuff. We've moved more Earth through mining and construction than all natural processes combined. These materials will leave traces in the geological record. Fourth, the bones. The most common bird in the fossil record of our era will be the chicken. We raise about 65 billion chickens per year. Their bones are everywhere. Future paleontologists will find the Anthropocene marked by an abundance of identical bird fossils. Fifth, a mass extinction signature, a sudden global disappearance of species. This is the marker that future geologists might find most striking. A die-off comparable in speed, if not yet in scale, to the great extinctions. The debate about when the Anthropocene began continues. Some say 1945. Others point to the Industrial Revolution in the 1800s. Others argue for the beginning of agriculture 10,000 years ago. What's not debated is that we're leaving a mark. We are the first species aware of our geological impact, the first capable of reading our own signature in future rocks. What we do with that awareness is perhaps the most important question facing humanity. This perspective can feel crushing. We're so small, so brief. The universe existed for billions of years before us and will likely exist for trillions of years after we're gone. We're not the point of the universe. We're an accident, a temporary fluctuation, a brief arrangement of atoms that will dissipate back into chaos. But I think there's another way to see it. The universe existed for 13.8 billion years before producing beings capable of understanding it. All that time, all those stars forming and dying, all that matter swirling into patterns and dissolving, and there was no one to witness it. No consciousness to appreciate it. No mind to ask what it meant. Then, in the last fraction of cosmic time, on one small planet orbiting one ordinary star, matter organized itself into beings that could look up at the night sky and wonder where it all came from. We are the universe becoming aware of itself. We are matter contemplating matter. Atoms arranged in patterns that allow them to think about atoms. For the first time in cosmic history, as far as we know, the universe has developed eyes to see and minds to understand. That's extraordinary. Not because it makes us cosmically significant in terms of size or duration. We're still tiny and brief, but it makes this moment precious. We're here now, conscious and aware, in a universe that spent most of its existence unconscious. This won't last forever. Our sun has about 5 billion years of hydrogen fuel left before it exhausts its core and expands into a red giant, likely engulfing Earth. Long before that, perhaps in about 1 billion years, the sun's increasing luminosity will boil away the oceans and make Earth uninhabitable for complex life. We have a limited time. Humanity might spread to other planets, other star systems. We might persist for millions or billions of years, or we might go extinct next century. We don't know. Our future is genuinely uncertain. But whatever happens to us, the universe will continue. Stars will keep forming and dying. Galaxies will keep colliding and merging. Time will keep passing, or at least the processes we interpret as time will continue. What happens in the far, far future? Cosmologists have thought deeply about this, and the picture they paint is haunting. For the next few billion years, the universe will remain recognizable. Stars will shine, planets will orbit, galaxies will slowly evolve. It's the stelliferous era, the age of stars. But this era will end. Stars form from hydrogen gas, and there's only a finite amount of hydrogen in the universe. As existing stars die and new ones form, the supply gradually depletes. In about 100 trillion years, the last stars will burn out. 100 trillion years. That's about 7,000 times the current age of the universe. It's an almost incomprehensible length of time. But eventually it passes. After the last stars die, the universe goes dark. No more fusion, no more starlight. What remains are the stellar corpses, white dwarfs, neutron stars, black holes. These dead remnants drift through an expanding, emptying universe. White dwarfs, the remnants of stars like our sun, will gradually cool over quadrillions of years. They'll fade from white to red, to infrared to nothing visible at all. They'll become black dwarfs, cold and dark, radiating nothing. If protons are unstable, as some theories suggest, then even these remnants will eventually decay. The protons and neutrons that make up all ordinary matter will gradually dissolve into radiation over timescales of perhaps 10 to the 34th years or longer. All the matter that makes up stars, planets, and everything else will eventually evaporate into elementary particles and radiation. Black holes will be the last remaining organized structures. They're remarkably stable, but even black holes don't last forever. Through a process called Hawking radiation, black holes gradually evaporate, losing mass as quantum effects at their event horizons release particles. A stellar mass black hole takes about 10 to the 67th years to evaporate. A supermassive black hole, like the ones at the centers of galaxies, might take 10 to the 100th years. After even the black holes are gone, the universe will be a diffuse sea of particles and radiation, spreading ever thinner through endlessly expanding space. Temperature will approach absolute zero. Nothing will ever happen again. No structure, no change, no events, just equilibrium, maximum entropy, heat death. This is probably our fate. Current evidence suggests the universe will expand forever, gradually winding down to this final state. Dark energy, the mysterious force driving accelerating expansion, shows no sign of changing. The universe appears to be heading toward eternal darkness. But here's something I find oddly comforting. Heat death is inconceivably far away. We have trillions of years before the last stars die. That's an almost infinite amount of time from any human perspective. And the far future will happen whether we worry about it or not. The universe doesn't need our concern. Our job isn't to fix cosmic timescales or prevent heat death. Our job is to live here, now, in this brief window when the universe is full of light and warmth and possibility. We exist in a rare moment. The stars are shining. Planets circle them. On at least one, life has arisen and consciousness has emerged. We can think, feel, love, create, wonder. This won't last forever. Eventually the universe will be cold and dark and empty, but not yet. Right now, in this cosmic instant, everything is alive. Here's a question that has haunted physicists for more than a century. Why does time have a direction? You know intuitively what I mean. The past is behind us. The future is ahead. Time flows from one to the other. Eggs break, but don't unbreak. People grow old, but don't grow young. Ice cubes melt in warm water, but warm water never spontaneously separates into ice cubes and hot water. We remember yesterday, but can't remember tomorrow. This directionality feels so fundamental, so obvious, that it hardly seems worth questioning. Of course, time moves forward. What else would it do? But here's the problem. The fundamental laws of physics don't distinguish between past and future. Take Newton's laws of motion. If you filmed a planet orbiting a star and played the film backward, you'd see a planet orbiting in the opposite direction. Both motions are perfectly consistent with Newton's laws. The equations work equally well forward and backward. Nothing in the mathematics tells you which direction is past and which is future. Take electromagnetism. Maxwell's equations, which describe the behavior of electric and magnetic fields, are time symmetric. A movie of electromagnetic waves played backward is just as valid as the forward version. Take quantum mechanics. The Schrödinger equation, which governs how quantum systems evolve, is time symmetric in the relevant sense. If you know the state of a quantum system, you can evolve it forward or backward with equal validity. Almost every fundamental equation in physics looks exactly the same if you replaced it with -t. The laws seem to allow the universe to run backward just as easily as forward. Watching a movie of fundamental physics, you couldn't tell if it was playing in the right direction. So why does the macroscopic world have such an obvious direction of time? Why do eggs break, but never unbreak? Why do we remember the past, but not the future? The answer lies in a concept called entropy. Entropy is often described as a measure of disorder, but that's not quite right. More precisely, entropy is a count of microscopic arrangements. It measures how many different ways the microscopic components of a system can be arranged, while still producing the same macroscopic appearance. Here's an example. Imagine a box of gas molecules. If all the molecules are clustered in one corner, that's a low entropy state. There are relatively few ways to arrange the molecules that would result in them all being in that corner. But if the molecules are spread throughout the box, that's a high entropy state. There are countless ways to arrange the molecules that would result in them being spread out. Here's the key insight. There are far more ways to be disordered than to be ordered. If you randomly rearrange the molecules, you're overwhelmingly likely to end up with a spread out configuration simply because there are so many more spread out arrangements than clustered arrangements. The second law of thermodynamics states that entropy tends to increase over time. Systems evolve from lower entropy to higher entropy. Ordered states become disordered. This isn't a law in the sense of a commandment. It's a statistical tendency. Systems don't increase in entropy because they're forced to. They increase in entropy because there are so many more high entropy states to move into. This is why eggs break but don't unbreak. An intact egg is a low entropy state. highly ordered, with the shell in one piece and the contents inside. A broken egg is a high entropy state, with shell fragments and contents spread around. There are vastly more ways for an egg to be broken than to be intact. So if you start with an intact egg and let random processes operate, you'll almost certainly end up with a broken egg. The reverse, fragments spontaneously assembling into an intact egg, would require all the molecules to randomly happen into an incredibly specific arrangement. It's not impossible, but it's so unlikely as to never happen in the lifetime of the universe. The increase of entropy gives time its direction. The thermodynamic arrow of time points from lower entropy to higher entropy. The past is when entropy was lower. The future is when entropy will be higher. But here's the deep puzzle. If the laws of physics are time symmetric, why does entropy increase toward the future and not toward the past? If you run the equations backward, entropy would increase toward what we call the past. The answer seems to lie not in the laws of physics, but in the initial conditions of the universe. The Big Bang was an extraordinarily low entropy state. All the energy of the universe was concentrated, uniform, and ordered. As the universe evolved, entropy increased, and it's been increasing ever since. We remember the past because memory formation increases entropy. Causes precede effects because that's the direction in which entropy increases. This is called the past hypothesis. The arrow of time exists because the universe started in a special, low entropy state. The direction of time is not built into the laws of physics. It's a consequence of how the universe happened to begin. But this just pushes the question back. Why did the universe start in a low entropy state? If high entropy states are vastly more common, why didn't the universe begin in equilibrium? What made the Big Bang so special? We don't know. This is one of the deepest mysteries in cosmology. Some physicists speculate about multiverses, where our universe is one bubble in an infinite foam of universes, and we happen to live in a bubble that started with low entropy. Perhaps in most universes, the Big Bang is high entropy and there's no arrow of time, no structure, no life. We exist in a rare ordered universe, simply because those are the only universes where existence is possible. Others propose that what we call the Big Bang was actually a bounce from a previous contracting phase, and that entropy increases in both directions away from the bounce. Time has no single direction in this view. There are two arrows pointing opposite ways from the bounce point. These ideas remain speculative. We don't have a satisfying answer to why the universe started with low entropy. But here's what we can say. Time's arrow is not fundamental. It's derived. The laws of physics are time symmetric. The asymmetry we experience, the fact that eggs break but don't unbreak, that we remember the past but not the future, that cause seems to precede effect. All of this emerges from cosmological initial conditions, not from the basic equations. There isn't just one arrow of time, there are several, and they seem to be connected. The thermodynamic arrow points from lower entropy to higher entropy. It's why heat flows from hot to cold, why ice melts, why organized structures decay. The psychological arrow points in the direction we remember. We have memories of the past, not the future. We know what happened yesterday, but not what will happen tomorrow. The cosmological arrow points in the direction the universe is expanding. Galaxies are moving apart, space is stretching, the universe is getting larger and emptier. The radiative arrow describes how electromagnetic waves spread out. When you drop a stone in a pond, waves radiate outward, not inward. When a star emits light, the light spreads in all directions. We never see waves spontaneously converging. These arrows all point in the same direction. Why? The thermodynamic and psychological arrows are clearly connected. Memory formation is a physical process that increases entropy. Recording information requires creating correlations between the memory system and the remembered event. And this correlation increases the total entropy of the system. You can only remember the past because memory formation requires entropy increase, which only happens toward the future. The connection between the thermodynamic arrow and the cosmological arrow is less clear, but they seem linked. The expanding universe creates conditions in which entropy can increase. If the universe were in equilibrium, there would be no arrow of time. The radiative arrow might be connected to the thermodynamic arrow through the initial conditions of the universe. Outgoing radiation increases entropy. Incoming, converging radiation would decrease entropy. We see outgoing radiation because that's the entropy increasing direction. All the arrows of time seem to trace back to the same source, the low entropy initial conditions of the Big Bang. There are more arrows of time than I've mentioned, and their alignment is one of the deepest mysteries in physics. The causal arrow is the fact that causes precede effects. You can influence the future, but not the past. Your decisions affect tomorrow, not yesterday. This seems so obvious as to hardly need stating, but why should causation work in only one direction? The fundamental laws are time symmetric. They don't prefer causes before effects. The quantum arrow relates to measurement and wave function collapse. In standard quantum mechanics, before measurement, a particle exists in a superposition of states. Upon measurement, the superposition collapses to a definite outcome. This collapse is irreversible in the standard formalism. You can't unmeasure something. Whether collapse is truly fundamental or an artifact of our description remains debated. But in practice, quantum measurement introduces irreversibility. The gravitational arrow is the fact that gravitational waves radiate outward, not inward. When two black holes collide, they emit gravitational waves that spread into space. We never observe gravitational waves spontaneously converging from all directions onto a point. Like light, gravitational radiation has an outward direction. But here's the truly remarkable thing. There's one place in fundamental physics where time reversal symmetry is actually violated. Just one. The weak nuclear force, which governs certain radioactive decays, violates time reversal symmetry. Specifically, certain particles called kaons decay in ways that are not symmetric under time reversal. If you filmed a kaon decay and played it backward, the rates wouldn't match. This CP violation, as it's called, was discovered in 1964 and won a Nobel Prize. This is profound. Almost everything in physics is time symmetric, but not quite everything. The weak force knows the difference between past and future. Is this connected to the other arrows of time? We don't know. Some physicists think CP violation might be connected to the matter-antimatter asymmetry in the universe. The Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving nothing. Instead, matter slightly dominated, and we exist. CP violation might explain why. If that's true, then this tiny asymmetry in one fundamental force might be ultimately responsible for our existence. The arrow of time, in some deep sense, might be why there's something rather than nothing. The connection between memory and thermodynamics goes even deeper. Let me explain why recording information has a fundamental thermodynamic cost. In 1867, James Clerk Maxwell proposed a thought experiment. Imagine a tiny demon that could observe individual gas molecules and selectively open a door to let fast molecules through one way and slow molecules the other way. This would separate hot from cold without doing work, apparently violating the second law of thermodynamics. For over a century, this was a puzzle. How does the second law survive Maxwell's demon? The resolution came from information theory. The demon needs to measure each molecule, storing information about its speed. This measurement process, and especially the erasure of information when the demon's memory fills up, requires energy expenditure and increases entropy. The demon doesn't violate the second law. The entropy decrease in the gas is exactly compensated by entropy increase in the demon's memory operations. This is Landauer's principle. Erasing one bit of information requires a minimum energy expenditure and produces a minimum entropy increase. Information is physical. Manipulating it has thermodynamic costs. Your memories are physical records, correlations between the state of your neurons and past events. Creating these records, establishing these correlations, is an entropy increasing process. Recording a memory requires making your brain state correlated with an external event, and this correlation comes at a thermodynamic cost. This is why you remember the past and not the future. Creating records is an entropy increasing process. Entropy increases toward the future. Therefore, records, including memories, point toward the past. Your sense of temporal direction isn't arbitrary. It's not a quirk of psychology. It's thermodynamically grounded in the fundamental physics of information and entropy. The arrow of time is written into the very process of knowing. Now, let me turn to an even deeper question. What is time, fundamentally? We've talked about how our brains perceive time. We've talked about how physics describes time. But what actually is it? What is the fundamental nature of time? The honest answer is we don't know. In relativity, time is one dimension of four-dimensional space-time, mathematically similar to the three dimensions of space. Mass and energy curve space-time, and that curvature is gravity. Time is woven into the geometric fabric of reality, inseparable from space. But time is clearly different from space in our experience. We can move freely in space, going left or right, forward or back. We can't move freely in time. We can revisit a location in space, but we can't revisit a moment in time. Space feels extended and available. Time feels like it's moving past us, carrying us along whether we want to go or not. Why is time so different from space, despite being unified in space-time? Some physicists think this difference is fundamental, built into the deep structure of reality. There's something genuinely different about the time dimension. The geometry of space-time distinguishes time from space through what's called the metric signature. Distances in time are calculated differently from distances in space. Others think the difference is an illusion arising from thermodynamics and psychology. We perceive time as flowing because of how memory works, because of entropy increase, because of the structure of our minds. But fundamentally, time might be just like space, another dimension in which all moments exist equally. In quantum mechanics, time plays a peculiar role. Unlike position or momentum, which are observables that can be measured and have quantum uncertainties, time is just a parameter. The Schrödinger equation tells you how quantum states evolve in time, but time itself isn't a quantum variable in the same way. There's no time operator. You can't have superpositions of different times the way you can have superpositions of different positions. This creates problems when physicists try to combine quantum mechanics with general relativity. In general relativity, time is dynamic. It curves and stretches. But in quantum mechanics, time is a fixed background. These two pictures don't fit together easily. When physicists try to combine general relativity and quantum mechanics into a theory of quantum gravity, they run into the problem of time. The equations of quantum gravity, in some formulations, don't include time as a fundamental variable. Time emerges from something deeper, or so these theories suggest, but we don't fully understand how. The problem of time in quantum gravity is one of the deepest puzzles in physics. Let me explain why it's so troubling. When physicists write down the equations of general relativity in a certain way, something strange happens. Time disappears. The Wheeler-DeWitt equation, the closest thing we have to a quantum equation for the universe, contains no time variable at all. It describes a static, timeless universe. How can a timeless equation describe a universe where things obviously happen, where time obviously passes? One proposed resolution is called the Page-Wouters mechanism, developed in 1983. It suggests that time emerges from quantum entanglement between subsystems. The universe as a whole might be in a timeless state, but if you're inside the universe, looking at only part of it, time appears. Imagine a clock entangled with everything else. The correlations between the clock's state and the states of other systems create the appearance of time. The clock reading 3 corresponds to certain states of everything else. The clock reading 4 corresponds to different states. From inside, this looks like time passing. From outside, looking at the whole, everything just is. Recent experiments have actually tested this idea. In 2013, physicists created quantum systems that exhibited the Page-Wouters mechanism. For an internal observer, time appeared to pass. For an external observer, the system was static. If time is emergent, what does that mean for us? It means the flow we experience, the passage from moment to moment, is real at our scale, but not fundamental. It's like temperature. Temperature is real and affects us, but it emerges from the statistical behavior of atoms. There's no temperature for a single atom. Similarly, time might emerge from quantum correlations. There might be no time at the fundamental level. This remains speculative, but it represents the frontier of our understanding. Time might not be woven into the fabric of reality. It might be a pattern that appears when the fabric is viewed from inside. Some approaches, like loop quantum gravity, suggest that space-time itself is made of discrete units, tiny granules of space and time woven together. There might be a smallest possible unit of time, about 10 to the minus 43 seconds, called the Planck time. Below this scale, the concept of time might not even make sense. Other approaches, like string theory, introduce extra spatial dimensions beyond the 3 we experience. Our 4-dimensional space-time might be a projection or slice of something higher dimensional. What we experience as time could be a shadow of more complex reality. The physicist Julian Barbour has proposed an even more radical view. In his timeless physics, time is entirely emergent. The universe consists of static configurations, moments frozen without duration. These configurations are connected not by temporal evolution, but by degrees of similarity. What we experience as the flow of time is actually a structure of relationships between static moments. Nothing moves, nothing changes. Time is an illusion generated by patterns of similarity between configurations. These ideas are speculative. We don't know which, if any, are correct. The fundamental nature of time remains mysterious. Let me address one final question. Could we ever travel backward in time? We've established that forward time travel is possible. Time dilation lets you skip into the future by moving fast or sitting in a strong gravitational field. This is physics, not speculation. But backward time travel is different. The equations of general relativity do permit solutions involving closed time-like curves, paths through space-time that loop back to earlier times, rotating black holes, certain configurations of cosmic strings, and some exotic space-time geometries contain these curves. In principle, following such a path would take you into your own past. Physicist Kip Thorne and colleagues explored how a wormhole might be used as a time machine. Wormholes are hypothetical tunnels through space-time, shortcuts connecting distant points. If you could create a wormhole, move one end at high speed, then bring it back, time dilation would cause the two ends to desynchronize. One end would be in the future of the other. Passing through the wormhole could take you backward in time. But there are enormous problems with this scenario. First, we don't know if wormholes exist or can be created. They're allowed by general relativity, but that doesn't mean nature produces them. No wormhole has ever been observed. Second, keeping a wormhole open long enough to travel through would require exotic matter with negative energy density. Such matter might not exist. Quantum field theory allows for certain negative energy configurations, but whether they could stabilize a wormhole is unknown. Third, quantum effects might destroy any time machine before it could be used. Hawking's chronology protection conjecture suggests that vacuum fluctuations grow without bound near a developing time machine, creating an infinite energy density that destroys it. The universe might actively prevent backward time travel. Fourth, there are the famous paradoxes. The grandfather paradox is the classic example. If you travel to the past and prevent your grandfather from meeting your grandmother, then you're never born. But if you're never born, you can't travel back to prevent the meeting. So you are born. So you do travel back. So you aren't born. And so on forever. Various resolutions have been proposed. The Novikov self-consistency principle suggests that any time travel that occurs was always part of history. You can't change the past because your trip was always part of what happened. You might try to prevent your grandfather from meeting your grandmother, but something would always intervene to ensure they met anyway. History is self-consistent. The many worlds interpretation offers a different resolution. When you travel to the past, you enter a different branch of the universal wave function, a parallel timeline. You can't change your own past, only the past of a parallel universe. The grandfather you prevent from meeting your grandmother is a parallel universe grandfather, not your own. These resolutions avoid logical paradoxes, but they feel unsatisfying in different ways. Self-consistency seems to constrain free will in strange ways. Parallel timelines raise questions about what these alternate branches really are and where you go when you travel. Most physicists suspect backward time travel is impossible. The chronology protection conjecture might be correct. The exotic matter might not exist. The paradoxes might indicate that backward time travel is not just technologically difficult, but fundamentally prohibited by the structure of reality. We can't prove it's impossible, but we have good reasons for skepticism. let me step back and reflect on everything we've explored. Time is not what we think it is. Our brains construct an experience of time that serves survival, not accuracy. We perceive a flowing present, a vanished past, and an open future. But this perception is riddled with distortions, manipulations, and outright fabrications. Our brains reorder events, stretch and compress duration, and create the illusion of unified moments from desynchronized sensory data. Physics reveals a different picture. Time is relative, not absolute. It stretches and compresses depending on motion and gravity. There is no universal now, no cosmic clock, no objective present moment. What seems like the flow of time might be an illusion, with past, present, and future existing equally in a four-dimensional block. The arrow of time, the asymmetry between past and future, is not built into the laws of physics. It emerges from the low entropy initial conditions of the Big Bang. Why those conditions existed remains mysterious, and the fundamental nature of time remains unknown. Physics describes how time behaves, but not what it is. Various theories propose time as emergent, discrete, illusory, or something stranger still. We don't have answers. How should we think about all this? How should understanding the true nature of time affect our lives? Here's my view. The strangeness of time doesn't make our experience of it less real or valuable. Yes, our perception is constructed. Yes, the present is in some sense an illusion. Yes, the flow of time might not reflect fundamental reality, but we still experience it. We still live moment by moment. We still remember the past and anticipate the future. We still age, lose people we love, create things that outlast us. The physics doesn't change any of that, it just puts it in context. Think about color. Colors don't exist in the external world. There's no redness out there, only electromagnetic waves of various frequencies. Your brain constructs the experience of color from raw sensory data. Red exists in minds, not in physics. But that doesn't make red less real to you. You still see red. You still respond to it. The fact that it's a construction doesn't diminish its presence in your experience or its importance in your life. Time is similar. Whatever time is fundamentally, whatever the physics says about block universes and entropy arrows and the relativity of simultaneity, you still experience the flow of time. You still inhabit a present that feels special, with a past that feels gone and a future that feels open. These experiences are real. They're the experiences of a conscious being in a universe that produces consciousness. The fact that physics describes reality differently doesn't erase the phenomenology of temporal experience. And understanding time can actually enrich that experience. When you understand that your sense of time speeding up is a trick of memory, you can fight it. You can seek novelty, pay attention to details, form new memories. You can stretch your subjective time by living more fully, encountering more experiences worth encoding. When you understand that the present moment is the only time you ever actually inhabit, you can appreciate it more. The past exists only in memory. The future exists only in anticipation. But now, this moment is where you actually live. Understanding this can help you stop dwelling in regret or anxiety and simply experience what's here. When you understand that your time is finite, that you exist in a brief window in a vast cosmic history, you can take that finitude seriously. You can stop wasting time on things that don't matter. You can focus on what you actually care about. You can recognize that the hours and days you spend are not renewable resources. Let me close with some practical thoughts about living well with time. There's a concept called the time billionaire. If you're 30 years old in good health, you have roughly 1.5 billion seconds of life ahead of you. You're richer in time than most billionaires are in money. The question is how you'll spend this fortune. Time is the ultimate non-renewable resource. You can earn back money, you can repair relationships, you can rebuild health to some degree, but time spent is gone forever. Every hour has an opportunity cost. Choosing one thing means not choosing everything else you could have done with that hour. The deathbed test is useful here. When making decisions about how to spend time, ask whether you'd regret this choice at the end of your life. The hours spent on busy work you don't care about, the years in a job you hate, the decades without pursuing what matters to you. These are the regrets of the dying. Research on happiness consistently shows that experiences bring more lasting satisfaction than possessions. We adapt to our stuff. The new car becomes just a car, but experiences become part of our story, our identity, our memories. They actually become more valuable over time as we reflect on them. Time is all you have. Spend it like it matters. Because it does. Time is strange. Time is mysterious. Time is not what we think it is. But time is also all we have. Every experience, every thought, every moment of joy or sorrow or wonder happens in time. Our lives are made of time. The universe has given us a small window, a brief span of years between non-existence and non-existence. The cosmic calendar runs for a year, and we exist for a fraction of a second at the end. We're recent arrivals on a planet that's existed for billions of years, in a universe that will continue for trillions more. But here we are, conscious, aware, able to understand our situation in a way no other species on Earth can. Able to ask questions about time and seek answers. Able to contemplate the mystery even if we can't fully solve it. That seems worthwhile. That seems worth the time. I don't know what time fundamentally is. No one does. The deepest physics points towards something stranger than our intuitions can grasp. Something that might not even resemble our experience of flowing moments. But I know that right now, in this constructed present, I'm using time to share ideas with you. And you're using time to consider them. We're two conscious beings, separated perhaps by distance and circumstance, connected by these patterns of meaning transmitted across whatever medium you're experiencing this through. The stars you might see tonight are ancient. Their light has traveled for years, decades, centuries to reach your eyes. The universe is old beyond understanding and will continue long after we're gone. But right now, you're here. You're conscious. You can think about time and wonder what it means. That's extraordinary. That's the universe becoming aware of itself, even briefly, even imperfectly. Don't waste it. Thank you for spending this time with me. If this exploration meant something to you, a like or subscribe helps me continue making these journeys into deep questions. Time is strange. Time is fleeting. Time might be an illusion. But whatever time is, we're in it together. Good night.